In this video, we look to make a better method than the one we have studied previously, the Euler's method. So let's jump right into it. We have an ODE, linear. We have y prime equals to something that depends on y and on t, and an initial condition. And we'd like to build a numerical method that is better than the Euler's method. So we start reminding ourselves that if phi t is a solution of the ODE, then it is a solution to the integral equation. That means that phi computed at tn plus 1 is equal to phi computed at tn plus an integral. The integral goes from tn to tn plus 1 and is the integral of f computed at t and phi. Phi computed at t itself. So this is not often very useful because it's a recurrent definition of phi, but we can still use it because we can try to approximate that integral. The idea of that integral is really that you're plotting f as function of t and phi, and you're taking the area underneath between tn and tn plus 1. And what we do when we use the Euler's method is that we approximate this area with a rectangle. We compute f at tn and phi tn, and we approximate the value of f at t phi t by the value it has at tn. So we draw a rectangle underneath. This is an okay way to compute a integral, but it's not particularly precise. We'd like to do something better. So the next thing we can think of is to try to make a trapezoid between the two. So now we're going to use information at tn and information at tn plus 1. And we're going to average the two in order to have a better understanding of the integral in there. So we're going to use 1/2 multiplied by h is the distance between tn and tn plus 1, multiplied by the value of f at tn, phi tn, and the value of f of tn plus 1, phi tn plus 1. So we're going to write it like this. It is better, but it has a problem that is implicit. We also saw the implicit Euler method. This is another version of an implicit method. We're trying to determine yn plus 1 depending on something, yn plus 1. While it does work, sometimes it's very computationally difficult to solve for this type of equations. It's possible, but you're losing some precisions just by trying to solve the equation itself. So it's often interesting to transform implicit methods into explicit methods. So we're going to replace yn plus 1 in our definition of yn plus 1 by the approximation we built in the Euler's method itself. So we have yn plus 1 is equal to yn plus 1/2 h multiplied by f computed at tn yn and f computed at tn plus 1 and an approximation of yn plus 1. And the approximation we use is the approximation that comes from the Euler method. So it's yn plus h f computed at tn yn. It's called the Hoyne formula. We can rewrite it to make it a bit more compact in some senses. It's a bit more of a general approach. We rewrite by defining, assuming we know yn and tn, we want to use this information to compute yn plus 1 and tn plus 1. So we define two middle steps, k1 and k2. k1 is the value of f at the beginning of our interval. So f computed at tn yn. While k2 is the value of f at the end of our interval with the approximation that we can build. So we have that k2 is f computed at tn plus h and yn plus h times k1. So yn h plus k1 is the Euler method, and we have plugged it in our right-hand side to compute a better approximation. Then yn plus 1 is defined as yn plus h over 2 k1 plus k2. And tn plus 1 is tn plus h. Writing it like this makes it also easier to change the value of h, because it's not every time we can pick a different h. But this is the formulation we usually prefer. It's a bit cleaner than what we had before. So we're doing more effort. Are we getting something better? Yes, we do. We have. One step local error of our Hoyne method is h to the third. While the global error is always one less than the local error, it's h to the second. Remember, local error is if you know exactly the starting point, what's the mistake you do after one step. While the global error is you have the starting point and you want to reach a certain time, and you take more and more steps to reach that time. And each step gives you more precision for every single length, but you also are doing more computations, so each time you're doing the error. So the global error is usually one less than the local error. So now we have h to the second as global error. This means that the Hoyne formula is a second order method. Also, I introduced this notation that is the wiggle, that means proportional to. The last topic of this week is the Runge-Kutta method. What we want to build is a fourth order method. And as we did for improving the Euler method, what we want to do is compute a better approximation of the integral of f computed at t phi t between tn and tn plus 1. During the improved Euler method, what we did was, instead of only using the starting point, so the value of f at tn phi tn, we also use the end point, the value of f at tn plus 1 phi tn plus 1. Here, we want to use that value as well, but we also want to use some middle points. So some values in between the two. So having yn and tn, we built this Runge-Kutta method. As for the Hoyne formula, we write it as steps. We call them stages. We write k1, that is the value of f at tn and yn. K2, that is an Euler approximation after 1/2 of h. Then K3, that is the Hoyne formula based on K2, so it's f computed at tn plus 1/2 h, and at yn plus 1/2 h K2. So we use a better approximation to compute K3, and then K4 is an approximation of the endpoint. So it's f computed at tn plus h, so we did the whole step, yn plus h K3. So we're using K3 to compute K4. And now that we have K1, K2, K3, and K4, we use all of them to compute yn plus 1. So yn plus 1 is equal to yn plus 1 over 6h, K1 plus 2K2, 2K3, and K4. Because we use 4 steps, they're called stages, this is called a four-stage Runge-Kutta. This is a graphic representation of what we did. We are trying to approximate the integral, the area underneath f t phi t, and we do that by getting more points along this function. We have k1, that is the approximation at tn. We have k2 and k3 that are both approximations in the center, and k4 that is the approximation at the end. The error of this Runge-Kutta method is locally h to the 5th and globally h to the 4th. That's why it's called the fourth order, 4-stage Runge-Kutta method. We usually shorten it up to the Runge-Kutta method because it's the most used Runge-Kutta method. If f does not depend on y, Then we can simplify things a bit. Then we have that yn plus 1 is equal to yn plus h over 6 of f computed at tn, 4 times f computed at tn plus h half, so the middle point, plus f computed at tn plus 1. And this happens to be the Simpson integration rule that has the same approximation errors as the Runge-Kutta method. So it does make sense to have these approximation errors.